Welcome back to the deep dive. Today we're taking a look at a problem that I think pretty much every single person trying to implement AI in a business context has hit head first.
Oh, yeah. It's a universal pain point.
Right. So you get the budget, you pick out this state-of-the-art large language model, you fire it up, and, well, it writes a beautiful, highly articulate memo about your quarterly earnings. But the numbers are just completely made up.
The confident hallucination, it creates a very specific kind of panic in the boardroom.
Exactly. And that brings us to the core problem we're unpacking from the source material today. We are dealing with this weird paradox with modern LLMs. They are incredibly intelligent reasoning engines, but their actual knowledge base is frozen in amber.
Right, because the training stopped.
Yeah, exactly. If you ask a base model about an event that happened, this morning, or ask it to summarize a confidential document on your internal server, it's legally blind.
I like to use the closed book exam analogy for this. A standard model is essentially a student taking a highly advanced test, but they are relying entirely on what they memorized years ago during their original training run.
They can't look anything up.
They can't look anything up. And the issue is, when they don't know the answer, they don't usually raise their hand and say they don't know. They improvise.
Huh?
Because fundamentally, they're designed to predict the next plausible word, not necessarily the true word.
So our mission for this deep dive is to figure out how we solve that. And we have a really fantastic stack of research here that outlines a hierarchy of solutions. It's kind of a ladder we can climb to make these models accurate, reliable, and domain-specific.
And ideally without spending $10 million training a brand new model from scratch.
Exactly. Nobody wants to do that. And we should be precise here before we jump in. We aren't just talking about tips to make a chatbot sound smarter. We are talking about fundamental architectural choices.
Right. We're going to start at prompt engineering, move up to fine-tuning, then get into RAG, which is Retrieval-Augmented Generation, and finally land on agentic workflows and hybrid architectures.
Let's start at the bottom rung of that ladder, the low-hanging fruit, which is prompt engineering. Now, I feel like everyone thinks they know what this is, like just write better instructions, be polite to the AI, but the research shows there's a lot more technical nuance to it.
Yeah, prompt engineering is fundamentally what we call in-context learning. You aren't changing the model's brain at all. You are just heavily curating the input to constrain and guide the output.
You're just giving it a really good instruction manual for that specific session.
Right. And the most effective technique here, which honestly still gets overlooked by a lot of beginners, is few-shot prompting.
This is where you actually provide examples in the prompt, right?
Exactly. So instead of just saying, classify this customer support ticket as urgent or low priority, you actually show it 3 historical tickets, 1 urgent, 1 low, 1 medium.
You show it the pattern.
You show it the pattern because the model is a massive pattern matching machine. It looks at those examples and mimics the logic immediately. And this is incredibly cost-effective. You don't need any complex infrastructure. You just need an API key and a well-written paragraph.
But there is a pretty hard ceiling on this, which the sources point out. I was reading about the goldfish memory problem in the notes.
Ah, yes.
Even with these massive context windows we have today, where models can technically read a whole novel in one go, they tend to forget instructions if they get buried in the middle of a massive block of text.
That's a known limitation called the lost in the middle phenomenon. If you take a 100-page corporate compliance manual, dump it into a prompt, and ask a highly specific question about a clause on page 50, the model often just glazes over.
It just misses it entirely.
Yeah, it pays very close attention to the very beginning of your prompt and the very end of your prompt. But that middle section gets incredibly fuzzy.
And I think the bigger limitation with prompting is that you can't prompt new knowledge into existence.
Precisely. You cannot prompt a model to know your Q3 sales data if that data wasn't in its original training set. You can only ask it to rearrange or reformat what it already knows. If you need it to know genuinely new facts, prompting alone is going to fail.
Okay, so prompting is cheap, it's fast, but it's limited. So let's move up the ladder. The next step actually changes the brain of the model, which is fine-tuning.
And this is a really significant jump in complexity. Fine-tuning means we are actually updating the internal parameters, the underlying weights of the neural network itself.
Okay.
We take a general purpose-based model that understands, basic English and logic, and we train it further on a much smaller, highly curated data set of input-output pairs.
The analogy in the source material that really stuck with me for this was from the IBM research, the chef analogy.
Oh, that's a great one.
Yeah, so the base model's like a decent home cook. They know how to chop an onion, they know how to roast a chicken. Fine-tuning is taking that home cook and sending them to a highly specialized culinary school for Italian cuisine.
Right, because after that intensive training, the chef has fully internalized those specific skills. They don't need to look at a recipe card to know that a risotto needs constant stirring. They just inherently know how to do it.
But here is where I want to push back a bit, putting myself in the shoes of someone building this. If I'm a business, why on earth would I pay to send my AI to culinary school? It sounds really expensive. Can't I just give the home cook a really detailed recipe card, which is essentially just prompt engineering?
You can, and for many things you absolutely should. Fine-tuning is actually rarely the right choice if your goal is just to teach the model new facts. It's really about teaching behavior or style.
Give me a concrete example of that.
Sure. Let's say you're building a tool for a hospital, and you need the model to output patient diagnosis codes in a very, very strict JSON format, using highly specific medical jargon. A general base model is going to constantly mess up the formatting. It's going to drop a bracket, or it's going to use a layperson term instead of the medical term. Fine-tuning locks that specific behavior in. It bakes it into the model's weights so that when it sees symptom X, it automatically and flawlessly formats it as JSON object Y.
So it's heavily about the form, the structure, rather than the raw content.
Exactly. In fact, if you try to fine-tune a model to learn facts, like say you feed it all of your 2023 financial reports hoping it will just memorize them, you run into a huge bottleneck.
Because it's still frozen.
It's still frozen. As soon as that fine-tuning run finishes, the model is out of date again. If a new report comes out the next day, it doesn't know about it.
And there's another risk mentioned in the notes that I want to highlight. It's called catastrophic forgetting, which, by the way, sounds like a terrible sci-fi movie title.
It does, but it's very real and very frustrating for developers.
What actually happens there?
Well, when you forcefully update a model's weights to make it highly specialized in one thing, you risk overwriting its broader general capabilities. So you might train it so aggressively on that JSON medical coding we talked about that it suddenly forgets how to write a coherent email or how to do basic conversational logic. You've essentially lobotomized its general intelligence just to get a rigid specialist.
Wow. Okay, so we have prompting, which is cheap but forgetful.
Mm-hmm.
And we have fine-tuning, which is great for style, but it's expensive, static, and carries this risk of forgetting things.
Mm-hmm.
That perfectly sets the stage for the architecture that has basically taken over the entire industry right now, RAG, Retrieval-Augmented Generation.
This is the real paradigm shift. With RAG, we move away from trying to force the model to internalize knowledge, and instead, we give it the ability to access knowledge.
It's the open book exam.
Yes, exactly. Instead of forcing the student to memorize a massive textbook before test day, we just give them a library card. When you ask the system a question, it first runs over to the library, finds the relevant pages, and puts them right in front of the model to read.
Let's look under the hood of that process, because the retrieval part seems to be where the magic actually happens. It's not just doing a simple keyword search like hitting Control F on a document, right?
No, it's much more sophisticated than that. Modern RA uses what we call vector databases.
Right, the embedding space.
Exactly. It takes all your company documents and turns the text into mathematical representations vectors that capture the actual semantic meaning of the words. So if a user searches for the word canine, the database knows to pull up documents about dogs or puppies, even if the specific word canine is nowhere in the text.
Okay, so just to make sure we're mapping this out clearly for you listening, the RAI workflow goes like this. The user asks a question, then the retriever searches the database and finds the relevant documents. Then the system pastes those documents into a prompt behind the scenes. And finally, the LLM generates the answer using only the information from those retrieved documents.
That is the standard Retrieve-Augment-Generate pipeline. And it brilliantly solves two of our biggest headaches. First, it drastically reduces hallucination because the model is grounded in the actual facts you just handed it.
Right, and it can cite its sources. It can say, hey, I got this from page 12 of the employee handbook.
Exactly. And the second huge benefit is data privacy. You aren't permanently baking your company's secret recipes or financial data into a public model's brain. You are just retrieving that data from your own secure database, showing it to the model for a split second in the prompt, getting the answer, and clearing it out.
But I'm looking at the critique of standard ARG in our source material, and there's a pretty glaring flaw highlighted here. The researchers call traditional R passive.
This is what we often call the garbage in, garbage out problem. A traditional R system is basically just a linear pipe. Water flows one way. If you ask a question and the retriever accidentally brings back the wrong document, let's say it pulls an outdated HR policy from 2019, the LLM doesn't know any better.
It'll just confidently write you a completely wrong answer based on that bad document.
Right. It just does what it's told. It assumes the context you gave it is correct.
It's acting like a compliant bureaucrat. It doesn't question the paperwork handed to it.
That's a great way to put it. It has no autonomy to look at the retrieved document and say, wait a minute, this is from 5 years ago. This doesn't make sense. And that limitation is exactly why we are currently seeing the massive rise of the next level in our ladder, agentic RAG.
This was the part of the research I found the most fascinating. We're moving from a passive pipeline to an active, autonomous agent.
We are moving from a pipe to a loop. An agentic system uses the underlying LLM not just as a text generator at the end of the line, but as the actual brain or the conductor of the entire process. It operates on what we call a reason-act-observe loop.
Let's walk through a concrete scenario for this. There's a server-down example from the Xcube LRBS case study in our sources, and I think it illustrates this shift perfectly.
Sure, let's look at that. Imagine an IT engineer-type server is down into their company's AI chat. Now, a traditional passive RAG system is going to search the vector database for the phrase server down. It's probably going to find some generic onboarding document that defines what a server is, and it will just regurgitate that definition to the engineer.
Which is incredibly useless to the person trying to fix the actual website outage.
Completely useless. But an agentic system handles that same query entirely differently. It receives the prompt server is down. But before it retrieves anything, the AI brain pauses and reasons. It says to itself, okay, I need to diagnose an active outage. A static definition isn't going to help here. I need to look at the live status logs.
So it generates an actual plan of attack.
Right. It decides to invoke a tool. It autonomously calls a check server status OPI. Let's say it gets back a response that says error 503. Then the agent observes that result and reasons again. It says, okay, error 503 means a traffic overload. My next step is to query the web traffic logs, and the loop continues.
It's autonomously researching the problem. It's not just grabbing the first PDF it finds and giving up.
And critically, it has the ability to self-correct. If an agent does retrieve a document and realizes it's completely irrelevant to the user's actual intent, it can literally critique its own work. It can say, this didn't answer the question, I need to rewrite my search query and try the database again.
It reviews its own work before it ever shows it to the user.
Exactly.
That sounds incredibly powerful, but I have to play devil's advocate here for a second. That loop process, reason, act, observe, self-correct, that sounds really slow.
It is. That's the major trade-off you have to accept. A traditional ARG pipeline returns an answer in milliseconds. An agentic RAG workflow might take 10, 20, even 30 seconds to reply because it's actively thinking, looping, and calling external APIs.
And what about the cost? Because you're hitting the LLM multiple times per query now.
The cost is significantly higher. Every single step in that loop, the reasoning, the tool calling, the reflection burns tokens, you are paying a premium for the model to think through the problem.
Okay, so let's synthesize where we're at. We have fine-tuning, which is great for internalizing a specific style or format. We have RG, which is amazing for injecting real-time facts. And we have agents for complex, multi-step reasoning. But looking at the cutting edge of the industry in these sources, it seems like the consensus is, why choose just one? Enter hybrid architectures.
Right, or what's increasingly being called RAFT, retrieval-aware fine-tuning. This is where we combine the strengths of these different approaches to cover their individual weaknesses.
The formula in the notes that summarizes this is behavior in weights, knowledge in context.
That is the ultimate mantra for modern AI architecture. Think about it. RG is wonderful at providing accurate facts in the context window, but standard-based models aren't always great at actually utilizing those messy, complicated facts. Sometimes they ignore the retrieved documents entirely, or they get confused if two documents have slightly conflicting information.
So you actually fine-tune the model specifically to be good at RG.
Exactly. You train the model on thousands of examples where its only job is to read a messy retrieved document and answer a specific question. You are heavily penalizing it during training if it hallucinates and rewarding it when it strictly adheres to the text.
You're teaching it how to read the context.
Right. You teach it, when I give you a giant block of corporate text, ignore the marketing fluff, focus only on the hard data, and format your final answer exactly like this template.
Okay, bringing it back to our earlier analogy. You're sending the chef to culinary school, not to memorize new recipes, but to learn how to efficiently read your specific, messy internal cookbooks and execute them perfectly on the fly.
That is a perfect return to the analogy, yes.
Before we wrap up, I want to briefly touch on a couple of technical optimization methods that kept popping up in the RAJS section of the sources. Because if we're actually building these systems, what makes them work well under the hood? The notes highlight chunking and re-ranking.
These are basically the gears that make the whole retrieval machine run smoothly. Let's look at chunking first. You can't just shove a massive 50-page PDF into a vector database as one single block. You have to break it down into smaller, searchable pieces or chunks.
But the size of those pieces matters a lot, doesn't it?
It matters immensely. It's essentially a Goldilocks problem. If your chunks are too small, let's say you break the document down sentence by sentence, you lose all the semantic context. The model might retrieve a chunk that just says, he clicked the button, but it has no idea who he is or what the button actually does.
If the chunks are too big.
Then you retrieve too much irrelevant text, you fill up the prompt with noise, and that lost-in-the-middle memory problem comes right back. So advanced engineering teams are now relying on what's called semantic chunking.
Which means?
It means using AI to analyze the document and break it apart at logical shifts in topic or paragraph breaks, rather than just blindly cutting the text every 500 words.
Okay, that makes sense. And what about re-ranking?
Re-ranking is your essential quality control step. Remember, an initial vector search might return the top 50 loosely relevant documents for a given query. But you obviously can't feed 50 documents into the LLM's prompt.
Way too much noise.
Yeah.
And way too expensive.
Right. So you introduce a re-ranker. This is a smaller, highly specialized model that acts like a remarkably strict grader. It reads through those initial 50 documents and scores them based on how well they actually answer the specific user's question. It picks the top 3 gold standard documents and ruthlessly discards the rest.
So it filters out all the distractors so the main LLM can just focus on the purest information.
Exactly. Implementing a re-ranker is often the single most effective, immediate way to improve a RAG system's accuracy.
Okay, we have covered the entire ladder. We've gone from simple prompting all the way up to autonomous agents and hybrid systems. Let's bring this down to earth for you listening. I want to build a rapid-fire decision matrix.
Let's do it.
If I'm a CTO or a lead developer listening to this, how do I actually choose? Scenario 1, I'm a startup, I have zero budget, zero infrastructure, and I just need a bot to help me write marketing emails in a fun, quirky tone.
Prompt engineering. Do not over-engineer this. Use few-shot prompting to show the model exactly what you mean by fun and quirky, and you're done. Your cost is essentially zero.
Perfect. Scenario 2. I'm a healthcare compliance company. I need to summarize complex patient records, and the output absolutely must be formatted in a legacy XML structure for our ancient hospital database.
That is fine-tuning. You need strict behavioral adherence to that XML schema. A standard RG setup might get the medical facts right, but it will eventually mess up the brackets or the tags. Fine-tuning ensures the format is locked in perfectly every single time.
Got it. Scenario 3. I'm an investment firm. I need a bot that can answer complex questions about global markets based on news articles that literally came out 5 minutes ago.
RAG. No question. You need dynamic, real-time knowledge. You cannot afford to fine-tune a model every 5 minutes when the market shifts. The book needs to be open, and the library needs to be constantly updating.
And finally, scenario 4. I need a system that can take a user prompt, research a competitor, crawl their live website, compare their pricing to ours in a spreadsheet, and then email me an executive summary.
That is agentic R. It's a complex, multi-step workflow that requires external tools, reasoning, and autonomous actions. A simple RAG pipeline can't crawl a website or execute a spreadsheet comparison. You need an agent to orchestrate that multi-step plan.
It really seems like the future isn't about one of these techniques winning out over the others, but about knowing how to combine them effectively.
Absolutely. The most powerful, reliable enterprise systems today are hybrid. They use agents to plan the workflow, RSG to retrieve the real-time facts, and fine-tune models to flawlessly format the final output.
Which brings me to a final thought I want to leave you with. We started this deep dive talking about LLMs as these static brains frozen in time. But looking at the evolution of agentic RE in these sources, we seem to be crossing a pretty massive threshold.
We really are. We are moving from models that just retrieve information to models that actively reason through problems.
Right. It's a fundamental shift from asking, what does the model know, to asking, what can the model figure out?
Exactly. When you give a reasoning engine access to tools, memory, and the ability to self-correct its own mistakes, you aren't really just building a chat interface anymore. You are building a synthetic coworker.
And that completely changes the role of the human operator. We go from being the provider of context to being the reviewer of the AI's autonomous work.
It's a totally different
It
paradigm.
is incredibly exciting and honestly a little terrifying to think about the implications of that shift.
Yeah,
But that is the nature of the deep dive.
it is indeed.
So evaluate your use cases, choose the right rung on the optimization ladder, and please don't pay to send a culinary school chef to chop an onion when a recipe card will do. Thanks for joining us on this deep dive, everyone. We will see you on the next one.
Goodbye.